So, okay. Rules of inference for quantified statements. Previously, we used rules of inference, the rules which are given in that table, to build arguments or to prove something or to reach at the conclusion. In all these examples, we are using those rules and we are reaching at some conclusion. But here we will do again the same thing maybe, but using a little bit different rules. Here, universal instantiation. Some rule is called universal instantiation. What is its logical expression? This is for every x p of x. If something is true for all the values of x, then that would be true for that. Here it is px. Px is true for all x. Meaning of this one. This statement px is true for all x. And if this C is in the same domain as the domain of X, then it means that PC is also true. It means the same thing. But as a logical expression, for every X, P of X, if this is true, if it is true, and if it is true and given to you, then it means that this statement P with some C, with some particular member in that domain is also true. This is mentioned here. Universal instantiation is the rule of inference. This is a rule. This is a rule, like other rules. Which means that PC is true, which means that this would be true. C is a particular member in the domain. And what is given? This for every X. This is given. For example, here, if there is a statement, all women are wise, which is equal to this above statement. He's enjoying that sentence. No, he said no. All women are wise. If this is the sentence, this sentence is, by the way, is by a wise husband. Okay, by a wise husband. So all women are wise if this is the statement. And if I say Lisa is wise, so this is true because Lisa is also a member of women. So now you will understand, but it is a rule, okay? So you have what is its definition? It is mentioned here. Now moving next, another rule. Universal generalization. Universal generalization. Here it is universal instantiation. And here it is universal generalization, which is the opposite of that previous one. For every x, px is now as a conclusion, and pc is as a given item. So how can we say that this for every x p of x would be true? By taking an arbitrary element. So that arbitrary means you have to take some random number from the domain. Some random number from the domain. And after taking that random number, if that PC is true, then you can say that, okay, this is true for all. This is again an inference rule, and it is called universal generalization. So up to now, you have to keep these definitions in your mind. Similarly, existential instantiation. It is like universal instantiation, but with existential. There exists x, p of x, and then pc. This is given, this is the conclusion. Or you can say this is premise and this is the conclusion. And how you can say it in terms of definition, it is written there. There is an element C. There we are talking first for this bottom line, okay? There is an element C in the domain for which this PC is true. If we know that there exists P of X is true. Or you can say If there exists P of X is true, then this PC is true for some elements, or therefore it's better to use the word therefore, because we are using the symbol. It is this one would be given, and this one, and if you have to, and it would be said that this given is true, and if it would be true, this premise is true, then we can say that PC is true for some element C. Anyhow, only you have to only use there exist. Rest of the things are almost same. Existential generalization. This is PC as a premise, and there exists P of X as a conclusion. For example, these are just the definitions. So now moving on the example where we are using these rules, and then you will understand better. Here, show that the premises, now the premises are given. Show that the premises, what is that one? Everyone in this discrete mathematics class, yeah, or you can say everyone in this class has taken a course in computer science. This is first premise. And Marla is a student in this class. This is a second premise. Show that the premises, this is the first one, this is the first one, up to this point, and this end, and this is the second sentence. Employ the conclusion. These premises gives us a conclusion. So now this is the therefore portion is started. Therefore portion is started. Marla has taken a course in the computer. So this is the conclusion. So these are in form of English sentences are given. A complete argument is given to you into the form of English sentences. Now you can solve it like that. But first, if you want to solve it by building argument, this is called building arguments. If you want to solve it like that, you have to first convert these sentences into the form of predicates or quantifiers or anything else, whatever is used there. So everyone in this discrete mathematics class. So I am representing this discrete with D of X. If X is in this discrete mathematics class, X is in this discrete mathematics class, we are going to represent it with D of X. Has taken a course in computer science class, so we are going to see computer science with C. X has taken the course of computer science. We are going to represent it with C of X. And then similarly, then the premises are now this sentence will become due to for everyone, for every X, D of X, X has studied this discrete mathematics class. Then whatever, everyone in this discrete mathematics class has taken a course. So if X has studied discrete, only then he studied computer. This is something hidden here. This concept is hidden here in this sentence. This concept is there or not? This concept is there or not? Everyone means X. In this discrete means everyone means X with universal quantifier. Everyone this discrete mathematics class, or you can say everyone in this class has taken course. It means who studied discrete must also has studied computer. So here I represented that thing there. For every X, D of X implies C of X. So X has studied discrete. If X has studied discrete, then X also has studied computer. And then what? What is that? Marla is a student in this class, which means Marla is a student in this class, discrete math class. Class is discrete math, okay? So that's why we can represent D into Marla. With respect to F, we have just replaced X with Marla because X is covering all, but we are talking here with only for Marla. And what is the conclusion? Marla has taken a course in computer science. So that is Marla C Marla. What is saying? Marla has studied computer science. So now actually you have done this thing. You can also conclude like that. This is your first thing. For every x, d of x implies c of x. This is your premise. This is your premise. The first portion of the, or you can say first compound proposition of your argument. Now use universal instantiation from 1. So this is line 1. Apply universal instantiation. What is universal instantiation? This one. If you have this form, you can write that general thing for some specific, for some particular person. And in our example, our particular example is Marla. So convert that x with Marla. D of x, convert that notation to D Marla and C Marla. And that for every symbol will go off. Because now we are with C, not with all x's. So now using this universal instantiation rule here on 1, we have this D into Marla implies C into Marla. Did you understand or not? Previously it is for all x's. According to universal instantiation, then PC is true. So now this is according to that PC. For that particular C. Now what? We have this D Marla already, which is a premise. This is also D Marla is given. Marla is a student in the class. So we are just writing that given information again because we want to do something with this 2 and 3. So we are just mentioning. Now we have this D Marla and C Marla and this third one D Marla. Now we can use the modus ponens rule on 2 and 3. And modus ponens is what? This is modus ponens. P and P implies Q, PP same, okay, Q is there. Just for memorizing, these are the tricks. Now, D Marla. So D Marla same, this will be the result using modus ponens. And what is that result is saying? Marla has studied computer science. That was your conclusion. So you started from here, from this, you started from your premises, and then you have reached your conclusion. There's another example in the book, example 13. Read it by yourself. And now we have another topic, combining rule of inference for propositions and quantified statements. For propositions and quantified statements. So you know universal instantiation. Previously, you know what is the rule for universal instantiation. For every x, P of x, C, and then PC. We know universal instantiation. And we know the modus ponens. Now we are going to combine these rules. We are going to combine this universal instantiation and modus ponens. For every x, P of x implies Q of x. This is something universal instantiation. This P of A is also this P of A. Combine these rules together. What are those rules? First one is this one. There is a concept of for every x, P of x, and then you have the PC. And what is modus ponens? P implies Q. So by combining those rules, for every x, p of x or q of x, and then p of a, therefore q of a. Did you remember that this is p implies q? This is maybe p, and then you have the q. So that picture of modest ponens and the picture of universal instantiation for every x, and this will therefore qa. You can consider the first statement and the last statement. You can leave this one. So that picture of modest ponens and universal instantiation is both there. What is this saying? For every x, if some statement for x is true, then that statement for q is also true. And P of A is what? Where A is a particular element in the domain. And here A is also a particular element in the domain. So now this is another rule you have, which is a combination of universal instantiation and modest ponens. So the other name for this is universal modest ponens. Similarly, we have, when you combine your universal instantiation and modest tolerance, you have this rule, universal modest tolerance. This is same with negation, but you have the negation. You have to keep these both examples in your mind. And okay, we will see this one, and then you will do, okay, there is no example for that. Okay, good. Assume that for all positive integers n, for all positive, so this is domain, for all positive integers, what are positive integers? 1, 2, 3, 4, 5, 6. If n is greater than 4, this might be p. Okay, let p of n denote n greater than 4, we are represent, okay, we will do it later on. If n is greater than 4, when the value of n is greater than 4, 5, 6, 7, 8, then n square, if you will take the n square is less than 2 raised power n. So if it is 5 square is 25, and 2 raised power 5 is 32. So 25 is less than 2 raised power n. Is true. If n is greater than 4, then this is true. It is given to you. Use universal modest ponens. So that one. Use this rule, which is universal modest ponens, to show that 100 square less than 2 raised power 100. So this would be the PC. This 100 is the C basically. Okay, we will see. So this is the domain for all positive integers. And if n is greater, so let P of n represent n greater than 4. P, here P means greater. You can represent it with G. N is, here P of n means n greater than 4. This n is greater than 4. And Q of n means we have to use, it is asked us to use universal modest ponens. So that's why we are doing this like that, P of n and Q of n. Otherwise, we will represent it with P and Q. Because this is in terms of P of x and Q of x. So that's why we are going into that form. P of n represent this, and Q of n represent n square less than 2 raised power n. This one, second portion. And we have the if and then. It means that in these two portions, P of n and Q of n, we have the arrow. We have the arrow. And this is the arrow here. In more. So then what? Can be represented by, for every n, P of n, Q of n. Now we have written for all domain. We have covered the whole domain. Domain is positive integers, we know that. We are assuming that this thing, this premise is true. We are assuming that this is true because it is given to us. Here it is written, is true. In the question it is written that this premise is true. So we are assuming it is true. Note that P of 100 is true, this 100 is given to us as a C, as a here in this formula for a particular element in the domain. It is given to us. So now we are taking that P100 is true because 100 greater than 4, because 100 is greater than 4 according to this condition. We are considering only greater than 4, not less than 4. So that feature is true, that property is true, that this 100 is greater than 4, not less than 4. Then now we are applying, so now this is our P. So these two things are now we have. Now we will apply this modus, universal modus ponens, and we will have the Q of A. And what is that Q of A? Universal modus ponens, this statement. This statement. Okay. Follows universal modus ponens, Q of 100 is true. And what is Q of 100? It is asked in the question. 100 square less than 2 raised power 10. If this it was asked in the question to prove this one, 100 square less than 200, and we are saying that 100 is above 4, not less. And if something greater than 4, then we said that n square is less than 2. And with previous discussion, we have made these two things in the question. And if we have made those two things correctly, this is true, then we applied this and we have this one Q of A, which is this one. And we are saying that this is also true by using that rule. Homework is given to you already. Today is the deadline. This is according to the last week. Okay, anyhow. And these are the further questions mentioned here that you have to practice only. Okay, I think this portion is now ended. And from inshallah in the next lecture,